Quantum sensors promise to change the way we measure the world around us, enabling numerous new medical and navigational technologies. However, many barriers remain to widespread adoption of quantum sensing into our everyday lives. Quantum sensing is a technique that uses the properties of certain materials at the atomic scale to make measurements with far superior sensitivity to the sensors we use every day. They already see usage at the cutting edge of research, but have proposed applications in medicine and navigation, such as enabling better non-invasive imaging. However, many barriers remain to widespread adoption of quantum sensing in our everyday lives, namely their operating conditions, which often require expensive and bulky cooling setups to work well. Recently, there has been work on organic molecules as quantum sensors, which offer a few advantages, as they are easier to work with at room temperature and easier to create in the first place. For example, materials like pentacene and paraterphenol combine to create a magenta crystal that has these properties. However, these crystals are still quite large and thus unsuitable for studying phenomena that occur on a very small scale, and tend to only be suitable for measurements in controlled lab environments. My research has been focused on creating a new kind of quantum sensor that resolves these drawbacks. It leverages 2D materials, which are materials that are composed of flat layers of single atoms, to protect the organic quantum sensor from the environment, while still being so thin as to not impact the measurement. By creating an envelope around the sensor, it also allows us to mold the sensor very thin to study small-scale phenomena. I developed a process to create these sensors by combining established techniques with novel innovations from our lab. I use a sticky gel to assemble the device by picking up each layer one at a time before placing it on a final holder. Such a device has never been constructed with organic quantum sensors before. Next, using a technique pioneered in our lab for studying metals, I used a sapphire hemisphere to apply a large pressure to the envelope and discovered that this technique could also be applied to my organic material to mold it to be extremely thin. Finally, I use a variety of instruments like our atomic force microscope or a Raman spectrometer to characterize the devices I made. For example, this device was greatly reduced in thickness after using our lab's approach, almost becoming invisible to the optical image. On the atomic force microscope, it shows not only that the material has spread out greatly in the envelope, but that it also has atomically flat precipices, indicating the presence of a crystal. We were able to characterize the signal emitted from the device before and after pressing, and it showed no significant degradation of performance, with both results agreeing with control measurements taken on the larger crystal. Atomic force microscopy showed that we could create devices down to 14 nanometers thick, which is 10,000 times thinner than a sheet of paper and 7 times thinner than the previous thinnest organic quantum sensor. In the coming months, I will continue to characterize these devices and their properties, as well as pushing to decrease the thickness even further down to the single molecule limit. It is my hope that my work will enable measurements never before possible, helping to prepare quantum sensing for everyday deployment. Thank you.